Let me make a little note about that, which means you could be asked questions about this on paper 3. So pay attention to some of the precautions and practical nature of doing these experiments, and don't get caught up too much in just the simulation part. You need to know some skills here too. We'll describe the use of capacitors and circuits qualitatively and quantitatively, and we'll make circuits to rectify AC signals, which we've seen already, but we'll review this. So, our review, we begin with a diode. Does anyone remember what is a diode?
It is the element that allows the current flowing on only one direction.
Yes, thank you, Jero. Perfect. It allows current to flow in only one direction, and easy enough, the symbol for the diode is an arrow that it kind of shows you the direction that it lets current flow. It is going to be to use a diode to make the simplest kind of rectifying circuit possible. So here, this is sending out current alternatingly back and forth. You can see the input voltage over here, sometimes positive, sometimes negative.
That's an AC graph.
Yes, this is the AC graph. Yes, you see AC source and the max voltage is 5.
Sine diagram.
So Tony, can you explain this graph over here?
So this graph shows the what? RMS?
It is showing the output. So that here's our load. This is resistor, the American symbol for resistor, and it's showing the voltage of this resistor. So let's compare these two graphs.
Why there's no negative in the second graph?
Yeah, that's the difference. Why is there no negative? Jero, can you explain that?
Let me think for a while.
Okay. So look at the diagram. You see the yellow dots? That represents the current.
Yeah, the current flow.
Yeah, and then it stops.
Yeah, because of the diode, it cannot flow back.
Yes, thank you, Jero. That's perfect. It's because of the diode. It only allows current this way. Circuit. Build this in physics lab. To do this, I'm going to stop sharing my screen, and I'm going to ask one of you to open up Circuit Lab and share your screen.
Maybe use this one.
Yeah, can. This is also a diode. The LED means light emitting diode, so this is a diode, but not the one I wanted to use. And there's just resistor, I think.
Here.
Oh yes, where was it? I still
It was just on the left of the LED.
Yeah.
Oh, I couldn't see the arrow, but yes, perfect. All right, you can get rid of this one. If you click it, click it, and then there's like a trash can you can put it in. You can get rid of it, or just put it to the side. It's okay. Now you also want to have here a resistor, just any kind of resistor, to make it look like the other circuit we had. Yeah.
This one?
Yeah. And now, click this. Click it, yeah. And then connect it to here.
Oh.
If you click it again, there's an X, and you can get rid of it, yeah. Perfect. And then from here to... Well, from black to red, you can connect it to the resistor. Yeah. Okay, good. Now, if you want to turn it on, you can. Yep, power button. And you can see the current flowing. Select
Oh yeah.
the resistor, click this, and then go up here and you can see some data about it and find the graph of the volts. Right, so it looks like the other simulation, right? We only see the negative part this time.
Yeah, maybe because the connect way.
Yeah, but you made your first circuit. Why do we want to rectify signals? Let me ask you guys, what are some reasons why do you think we want to rectify a signal? Anyone have any ideas?
Because we don't want the negative part.
Yeah, I mean, exactly. Like, negative and positive refer to directions, but it means we want only one direction. There are some devices that will not accept two directions.
So there's no current go back.
Yes, good. So this is something we want to do, but...
And in the transmission of the power, if you are in AC, you will lose more energy than DC.
Yeah, another reason too. We're going to lose power. But we also...
What about that? Because DC can store current.
Well, DC is direct current, but you said store current, and that's something we are fast approaching. It's kind of on my next couple of slides. How can we recover more of the input power? And we're going to do kind of a mini project this week where you will investigate how to get the most out of an AC power source. You can use Physics Lab or another simulator. You could make your own. This could be physical circuit if you have the materials. All right, your homework, we have just enough time to introduce this, is going to be to use Physics Lab to build a full wave rectifying circuit. You saw this circuit when we finished studying power generation in 11.2, but it's a little bit more complicated, so it'll take you a little bit more time. I made several mistakes when I tried it because so many connections, it's so hard to do. But you will use 4 diodes connected like this so that you get all of the AC voltage. It's not smooth, but you get all of it.
So, here, can you see my finger?
Yep.
Yeah, here, it is plugged to a oscillator, actually. So, like I said, it's a oscillator, so it's sending out the pulse of electricity in period, and like there are current and no for like take turns, and here is the inverter for giving the electricity at both times. So I turn the DC into AC here. Use this chip. And these black small elements are the diodes, and we can see that it is very simple to be seen, I think. Could you hear me?
Yeah, you're doing a good job.
Yeah, and here is another one that I make it more visual, so I use LED instead of the diodes. And here you can see that the diode is the LED is actually take turns to light it up.
Yeah, really cool. So awesome job, Jero. You are going to look at a homemade capacitor. So it doesn't have to look like these guys you see in circuits. You can make a capacitor on your own.
It could be a square.
Yep, it could be a square. Here it is. That's the same as electric field. So when that happens, what is the maximum charge? So you will want Q. You should know C. Can you figure out as a middle step?
Let's see.
Yeah?
So the plastic is dipole or not dipole?
That is a good question. Yeah,
A
it
weak
does.
dipole.
It does form dipoles inside the material. You're ahead of me. It's on like several slides away. You can see what's going on inside of the plastic. But really good question, Tony. Yeah, that's what's going on. That's how it's helping the capacitor store charge. Very good question. All right. So do you guys know what to do in the breakout rooms? I'll copy and paste this into WeChat also so you can have the instructions. So estimate together, come to an agreement, and then we'll see which group, my computer's too slow, has good estimates. If they're the same, are they very different? We just want to estimate.
It seems this area is not very big, like compared to the
How many?
ammeter. Is that ammeter or something?
Yeah, it's an ammeter.
Yes, so it's like about 15 ammeters areas big.
Oh, good way to do it, yeah.
Yes, so might be. Yeah, I don't have a clear concept about it. Maybe it's about 1 meter square. No, not that big. Half meter square might be.
Yeah, I think a half meter squared is a really good estimation. You can do that. Yeah. All right. I've got to go do nucleic acid tests now.
Why isn't it a straight line instead of a curve?
Oh, okay. Awesome question, Ocean. This is we're going to be getting to this in a little bit. We're going to see actually that this curve is an exponential relationship. It's not a straight line. And it's related to the same reason radioactive decay is not a straight line. And here's the reason. We said that when any process, any changing process is related to the thing that's changing, we get the natural number E in that relationship. So I'm going to, this is for discharging, but coming back to here, right? So in the beginning, the rate of change of the charge is very high. This is big in the beginning. Because Q is small. Right? When there's no electrons on the plate here, at the very, very beginning, the current, the change in Q, is going to be very large because they're going to be trying to balance out the electric field from the battery. The electrons are going to be rushing to kind of balance out this positive and negative. But then the amount of Q is going to increase, so the effect is not as big anymore. So the change in Q is going to become less. It's not changing as quickly in the beginning. And then finally, there is no more current because the electric field from the battery is canceled by the charge that built up on the plates of the capacitor. So after some time, the capacitor's voltage is like canceling the EMF. Enough charge built up to cancel the battery's EMF. That was such a good question. I hope that helped a little bit. Does that explain?
Yes.
No, try again.
Okay.
Yeah, it fixed.
Okay, so let's go back and let's look at the voltage of the capacitor. Let's see it charge up and discharge again. See how fast it is. Okay. Let's
Okay,
increase.
still fast.
Let's try to change C again, but not quite so big. One C
Okay.
is very, very big. Maybe like, yeah, that one. 10 microfarads.
Like this one?
Yeah.
Yeah,
Ah.
kind clearly.
Yeah. Try like maybe like 100 now.
Okay.
100 microfarads.
Yeah, this
Yeah.
one is clear.
Yeah, this one is very clear.
Yeah.
So, okay, thank you, Alex. I think you can stop sharing your screen now, and let's think about
Okay.
what you showed us. What factors can we do to change how quickly it charges and discharges? What is the effect of V?
Maybe no.
Yeah, I agree. There is actually no effect. What about R? David, what effect does changing R have on the time it takes to change?
R is bigger than.
Like, was the graph
Bigger?
Yeah, when R is bigger, the time it is bigger. It's
Is
more like
longer?
longer time.
Yeah.
It's more like this one and not like this one. That one is short. This one takes a long time. Good. And Alex, what about increasing the capacitance? What effect does that have?
Increase the capacitors is just like make the change of V slower.
Yeah, longer time. It increases the time of changing.
Yes.
Yeah, and R and C actually characterize the time change for these circuits. Look up a type of circuit called a voltage multiplier circuit. These are actually more simple to build than the full wave diode bridge. They are called voltage multiplier because they're going to rectify, so make it AC into DC, and also increase the output voltage like a transformer does. Transformers can increase voltage. We can use capacitors to do this too.
It's about like how does the voltage get multiplied? As we saw before, it can be multiplied by increase, like this kind of a set of parallel circuit contains a capacitor and a diode that is in a series with other parallel circuits. Oh. And multiply the power output too with this circuit. The answer is it can be increased, but like I think the energy can be conserved perfectly, and also the current will just not multiplied with the voltage, so it can be increased.
Well, we think back to your other side. You said that we have to have like big resistance and really low current. Or if you
Yeah.
have high current, the voltage drops.
Yes.
So it's like choose one.
So like it can be increased, but cannot be like that, like voltage multiplied. It cannot just work like this.
Yeah, we'll come back to
And
this question at the end.
So high frequency from the AC source will likely have better results It might because discharging time on the handset of AC source is lower due to its high frequency.
So the AC frequency does not affect the discharging time, but
Oh,
if the discharging time is like set, if the
Yes.
AC is changing more quickly, then
in the same unit time, it can work more.
yeah,
Tripler. This
yeah.
one tripler.
So this
So-
one,
Firstly, this is the AC supply.
yeah, and then hold it there.
Oh, God.
These two are for AC.
Oh, okay.
So this is output. This is input.
Oh, this is input. Maybe this one is connected to here, and this one.
You want to delete the battery, yeah.
Yeah. So it's like this, maybe,
Then we can try it.
and it is open.
Yeah, turn it on.
Ah,
Oh, see, now you're getting a lot more voltage.
yes.
Yeah, so this one has what, 1, 2, 3 capacitors. So your input is maybe multiplied by 3.
Yeah,
Yeah,
it seems multiplied by 3.
yeah. So good job.
Okay,
It's it's working
so
right
the circuit
away.
is fixed.
Yeah.
Yeah, but yeah, as I said before, the AC source is actually made by the DC in some kind of special way. But yeah, but it really doesn't matter for this.
Uh-huh.
Yeah, can you? Oh, it is mirrored. But yeah, as you can see that it is actually floating up and down, but it's around the 10 volts.
Mhm.
And like looking here, it is for adjusting frequency for the AC, and we can see that as it goes higher frequency, like you can see now it is stable and
Oh,
like
that's really,
stabilized, and here is 9 volts.
yeah, that's actually really interesting. So when it was changing, it was low frequency.
Yeah, so if the frequency goes down like this, yes, as you can see, it starts to become more unstable. And the reason for that it is stabilized as 9 volts instead of 10 volts, which is doubled for the 5 volts, is because of that here diode may consume some of the energy that is given by the current. So here is not a ideal situation that is 10 volts instead. It is like 9.1 only.
Yeah, that's true. There's some energy lost in each stage when you build these. Yeah, that's really great. So yeah, that's a good demo of showing how the frequency affects it, right? Because low frequency, they have time to discharge more, it's more unstable. Awesome,
Yeah.
Jero. Thank you.